and today I'm going to run through a few undergraduate, upper high school level chemistry questions. So here's our first one for today. Separate this redox reaction into its balanced component half reaction. So I'm just going to rewrite the reaction here. And we know it's a redox reaction because on this side, the charge on chlorine is 0. We can check the formal or the oxidation state on each of the constituents by just comparing the total charge and using some of our rules. So here, because chlorine is a pure substance, it's going to be 0. Here it's just sodium, so the total charge, it's going to match the total charge, which is 0. And then here we've got NaCl, and halogens will typically be -1, and alkalis will typically be +1. So that's going to be the formal charge there. So we've got a change in charge state, so, and that is what happens during a redox reaction. So to split them into their component reactions, we split up the 0 to -1 and the 0 to +1, or as they're called, we split up the oxidation reactions and the redox reactions, or reduction reactions. Okay, so once we've split them up like that, we balance them by adding electrons to the appropriate side. The side that we add the electrons on is always going to be the same no matter whether it's the oxidation or reduction. So for every oxidation, it'll always be on the same side of the reaction. But just for explanation purposes, the side we're going to add it on will always balance the charge. So on this side of the reaction here, we have 0 charge. On this side we have +1, so that means we need an electron. And here we have 0 charge, and on this side we have -2, so we need +2 electrons. And then when we balance the redox reaction, we need to balance the number of electrons, so that means this guy needs to be multiplied by 2 throughout. The clue, of course, was given in the original equation anyway, but that's okay. And then we just sum the two reactions, canceling out the electrons where appropriate. So here we're going to cancel 2 with 2, and we're going to sum them and get 2Na plus Cl2 goes to 2Na plus 2Cl minus, which is basically what was given in the original expression anyway. I just wanted us to separate them. So these are the two separate equations. So that's the oxidation reaction and that's the reduction reaction. And just to be sure that they're visible, so there's our oxidation and our reduction. And we're assuming it's in neutral condition, but it actually wouldn't matter if it was in acidic or basic in this case. Okay, so there's our reduction, and our oxidation. So this looks correct. Yeah, okay. I'm just gonna grab a new one. Okay, so what is the product of the reaction below? So in this case, we've got, you can't see the reaction, but I'm just going to draw it out. So we've got HC, H3C, CH3 plus HBr. So here we've got a halogen and an alkene, and so we're always going to get attack of the halogen at one of these two spots, and because the alkene is symmetric, so it'll be on the carbon adjacent to the pi bond here, and because it's symmetric, it could go in either spot. And so then the final structure, it's going to open up the pi bond to give you a bond to a hydrogen, and then the bromine will donate a bond. So then the final structure will look like, I should try it better than that. The final structure will look something like where I've used these dashes and wedges to signify that they're coming out of the page or into the page. And I'm putting the CH3s as far away from each other as possible. I assume that they would be the most repulsive. And so the final structure would look something like this. So depending on whether it comes from the top or the bottom would be the ordering here, or depending on which side of the double bond it attacks will also depend on this. So it could be that, or it could be or it could be this. So it could just be basically swap the bromine hydrogen positioning. And so that really doesn't change much and wouldn't be observable, but these are, so in this case, right, from high mass to low mass goes around this way, whereas this time it goes this way. So it's changing the, these are actually enantiomers, right? So they're non-superimposable mirror images of each other. But you'd get both in equal measure, and also the other side. But those would be, those would not be enantiomers. Those would be symmetric. Okay, so let's look at the solution here. So that's what we get. So it doesn't really matter where it goes. Yeah. So that looks good. Okay, sulfur hexafluoride is an extremely dense gas. How does its density compare with that of air? Okay, so to get the density of a gas, the best place to start is the ideal gas law. Now we have in here the number of moles, and a volume. Remember that density is mass over volume. And we know how to get mass from moles. So our molar mass is our moles over our mass, or moles is mass times molar mass. So that means our ideal gas law can become PV equals M RT, where little m is our mass and big M is our molar mass. Or rearranging this, we can write it as P over MRT. Wait, did I do that wrong? Yeah, I did do it wrong. Oops. Let's look at this. It's like, that doesn't look right. Oh, that's what I did wrong. Alright, backtracking a little bit here. Sorry, molar mass is mass over moles, so moles is mass over molar mass. There you go. And so that's mass over molar mass. So then this is up here. Get rid of that. My apologies. Alright, so P times the molar mass over RT is mass over volume. And that is equal to our density, right? So mass over volume is our density. So from our quadratic equation, we can get, or from our ideal gas law, we can get density as PM over RT, where M here is the molar mass. This is our pressure. That's the ideal gas constant. And that is the temperature. So in this case, we're not given any of these conditions. And I always tend to use just the normal values of pressure and temperature. So I'm going to use 1 atmosphere. And T equals 20 degrees Celsius, which is 293.15 Kelvin. You might need to use standard temperature and pressure, which is slightly different from these values, specifically the temperatures at 0 for standard. But that doesn't make any sense to me because we don't live at 0 degrees. Although might be more applicable to actually to right now, where especially in Canada where it's closer to 0 degrees, but 20 degrees makes sense to me. So I'm going to use that. The molar mass for SF6 can be found from its constituents. So molar mass of sulfur is 32.065 grams per mole. Molar mass for fluorine is 18.998403 grams per mole. So the molar mass of SF6 is the molar mass of sulfur plus 6 times the molar mass of fluorine, which when we run this through on our calculator comes out to 146.055418 grams per mole. Okay. And the ideal gas constant in those units is 8.314 liters atmospheres per mole Kelvin. Okay, so then putting all that into our density expression, and I'm just going to rewrite it here and migrate stuff down a little bit so that we have it. So our density is, again, just as a reminder, mass over volume, which is our pressure over our T times our molar mass. I'm writing it like this just because it wants us to compare it with air, which just has a different molar mass, but we're going to use the same pressure, R and T, so might as well turn that into its own little constant. So that's 1 atmosphere over 8.314 liters atmospheres per mole Kelvin times temperature, which is 293.15 Kelvin, and then times the molar mass. All right, and so then our density for SF6 is, running this stuff through on our calculator, we find it's around 4.102986 times 10 to the minus 4. Atmospheres will cancel, kelvins will cancel, and leaving moles per liter. And our molar mass for SF6 was found as 146.055418. Moles will cancel, leaving us the grams per liter, which is a density, so that's good. And we get 0.059926 grams per liter, which is 0.0599. Not really picking significant digits for any particular reason, since I'm not really given any in the question other than for air, but I put it to 3, I suppose, just to compare with air. So now for air, we can do the same thing, but like I said, it's going to have the same P over RT, so that means this will be the exact same. And so we just need to change our molar mass, which is 29.0. And then if we run this through, we get a density of 0.0119 grams per liter. And so then we can say that just by looking at the values, that the density of SF6 is significantly more. We can divide the two. And say that the density of SF6 is about, finishing writing this out, is about 5 times greater than that of air. So SF6 is about 5 times more dense than air. Okay, so looking at the solution here, they're using mm for molar mass, I suppose. So using the ideal gas law, splitting it out for density and our like terms, plugging in values. The density they get is 6.5. Oh, I guess. No, I still don't get where that would come from, but okay. Oh, I guess liters atmosphere per Kelvin mole. Oh, did I use the wrong gas constant? Oops. I don't think so, though. No, I think that's the Tor value. That I'm going to have to look into. But hilariously enough, you still get that it's 5 times more. Because you still get that it's 5 times more because it really just matters about the ratio of their molar masses, right? So if you divide the two, and that one, don't memorize the gas constant, unfortunately. I'm fairly certain I'm correct here. But in any case, like I said, it doesn't change the answer, which is that the two are 5 times different. But I will need to check on the value of the gas constant. So I'm just going to actually double check that. Oh, okay, so it is liters. Well, that's my mistake. Oops. Okay, so yeah, so that's my mistake. So the R that I used is actually not the correct one. Sorry about that. But although the math comes out slightly different and the values come out a little different, it's all the method is correct and the same. So I'm just going to say the solution is correct here, and go forward. Okay. Okay, so we've got a 0.3178 gram sample of potassium hydrogen phthalate. So that would be KC8H5O4. We've dissolved it in 100 mils of water. Does that matter? Okay. We've dissolved it in 100 mils of water. We need 33.75 mils of sodium hydroxide solution to reach the equivalence point. What is the molarity of the sodium hydroxide solution? Okay, so yeah, I don't think we need that. Okay, so this the potassium hydrogen phthalate is going to give us K plus the hydrogen phthalate ion. Our hydrogen phthalate ion is going to react with water to give us the phthalate ion plus H3O plus, and then sodium hydroxide is going to give us Na plus OH minus, and OH minus is going to react with H3O plus to give us water. All right, so our net reaction here, now I've balanced everything here. So our net reaction is we're going to cancel these, cancel our waters, cancel our H2O pluses, and so our net reaction is just going to be that KC8H5O4 plus NaOH is going to give us Na plus, oh, that's what I did wrong. So that would actually be 2 waters. Na plus C8H4O4 2 minus plus water. Yeah, okay. So that's kind of our neutralization reaction. And so we have 0.3178 grams of this guy. And our neutralization occurs in a 1-to-1 ratio. So for each mole of our potassium hydrogen phthalate, we need a mole of NaOH to neutralize. So that's going to be how we're going to calculate the molarity in the end, is just by using that 1-to-1 ratio. So for our potassium hydrogen phthalate, we need our molar mass. So the mass of potassium is 39.0983. The mass of carbon is 12.0107. The mass of hydrogen is 1.00798. And the mass of oxygen is 15.9994. All right. And I don't think we need the molar mass for NaOH, but if we do, we'll calculate. All right, so the molar mass, the molar mass for potassium hydrogen phthalate is just the mass of potassium plus 8 times the mass of carbon plus 5 times the mass of hydrogen plus 4 times the mass of oxygen. Which, if we put in the appropriate values and run them through our calculator, we get 204.2214 grams per mole. Okay, so then we're given that there's 0.3178 grams. So the number of moles of potassium hydrogen phthalate is just the mass over the molar mass, which is 0.3178 grams over 204.2214. And checking our units here, the grams will cancel, the moles will come up, so that's good. And so our moles are 0.001556 moles. And so, because again, it's in a 1-to-1 mixture, that is equal to the number of moles of NaOH that we'd added to equalize to reach our equivalence point. So that means that NaOH is equal to 0.001556. And it's asking for the molarity of the sodium hydroxide solution. So just the 33.75 mils, not the 100 mils. So just the solution that was added. So then the concentration of NaOH is just this molar amount over the volume. And molarity is in moles per liter, so we want to multiply by 1,000 mils per 1 liter so that the mils cancel and we get moles per liter. And so this comes out to be 0.04611 moles per liter, or keeping it to 4 significant digits, I guess. 44.0 611 times 10 to the minus 2 moles per, or representing it as molar. Alright. And, okay, so calculating the molarity. So I don't think we need to do that, we just need the number of moles. Okay, so substituting the values. Oh, okay, so it comes out to be the same number, which is good, but the way the person who solved it did it was to say that the molarity of our C8H5KO4, or our potassium hydrogen phthalate, must equal the molarity of the NaOH, which is true. And then using the ratios of the volumes, but it comes out to be the exact same. Solution is correct. Just going by a concentration route as opposed to a molar route, but that's still correct. Okay, so we're asked to balance this redox reaction in acidic solution conditions. So here we have, I'm just going to write out the reaction. So S2O3 2 minus plus copper 2 plus goes to S4O6 2 minus plus copper plus. I'm just going to migrate this down a little bit. Okay, so in this case, we can readily identify that copper is being reduced. It's less obvious that this species is being oxidized, but if we consider the partial chart, the oxidation states, right? So on oxygen, it would be 2 minus each. So the sulfur must be being oxidized. But in this case, I don't think it's that easy. Because I think I talked myself into a hole there. Because yeah, so the sulfur. So there must be something funny there with the oxygen charge. But this guy must be being oxidized. So we're going to just split it into our separate half reactions. So again, our copper reaction, our copper is going to our copper plus. And we need to, it's being reduced, but we need to balance our charges. So 2 plus goes to plus, so we need an electron on this side. That way we have 2 plus minus 1 gives us positive on the left, and we have a positive on the right. So the charge is balanced. And then our oxidation reaction, so S2O3 2 minus goes to S4O6 2 minus. And in this case, we want to balance. So the first step in balancing is going to be to balance all the elements besides oxygen or hydrogen. So we're going to need 2 of these because of the 4 sulfurs, and then we can look at the oxygens, and now we have 6 oxygens here and 6 oxygens here. So now we don't need to worry about anything else. We need to balance the charge, so there's 4 negative charge on this side and only 2 on this side. So we're going to need 2 electrons on this side. Now we need to balance our 2 half reactions by the number of electrons. So this one has 2 electrons, this one just has 1. So we need to multiply this guy by 2 throughout to balance the electrons. And now our our balanced equation is just by summing these two, canceling the electrons. Then we get 2 copper 2 plus 2 S2O3 2 minus gives us 2 copper plus S4O6 2 minus. And that's our balanced redox reaction. And again, it being acidic or basic doesn't matter here, only because there wasn't spare oxygens or hydrogens. But that's our balanced reaction. So going through the solution, we started with the copper. We balanced these guys. We get our electrons balanced, and then we sum, and we got a couple swappings in places here. Is it S3O6 or S4O6? Yeah, S4O6. Whatever, it's okay. So the solution is correct. There's just a small typo on the sulfur there, but that's fine. Okay. So for this one, I guess this is my 6th one, now that I've been numbering. If calcium chloride is dissolved in water, what can be said about the concentration of the calcium 2 plus ion? Either it has the same concentration as chlorine, its concentration is half that of chlorine, or its concentration is twice that of chlorine. So if we dissolve CaCl2, we're going to get calcium 2 plus 2 chlorine ions. And so if we look at the mole ratios here, for every 1 mole of calcium, we have 2 moles of chlorine. So that means that our N calcium is going to be a half that of N chlorine, right? Because we have double the amount of chlorine as calcium. And so if we look at our solutions, our answers that we can choose, so it's not the same, but its concentration is half that. So it'll be B, concentration is half. And I should finish that off by saying that concentration is N over volume, but of course if NCA plus is a half NCl minus, then the concentration is indeed half, as the volumes will be the same. Checking the solution here. The balanced equation is this. From the stoichiometric coefficients, we can tell that the moles of calcium will be half that of chlorine, and so the concentration will be half. That looks good. Okay, so now we're going to balance this redox reaction in acidic solution. So the products of this reaction, I'm just going to scoot this down, will be zinc 2 plus sulfur plus NO yep. Okay. And now it's less obvious what's happening here, but zinc is going to be a +2 charge in this compound. So zinc is one of the alkali earth metals, so it's basically always +2. So sulfur is -2. Here on this side, zinc is still +2, so essentially nothing's happening to the zinc, but the sulfur is going to 0. So our sulfur is being oxidized as its charge is going from -2 to 0. And on this side, the oxygen is -2. And so the nitrogen must be the rest of the charge, right? So the charge here is -2 times 3, which is -6. But the whole thing needs a -1. So that gives the nitrogen a +5, right? So the charge has to balance, so that means that for the NO3, we've got +5 plus 3 times -2 equals -1. 3 times -2 is 6, so 5 minus 6 equals -1. -1 equals -1. So that looks good. And then on this side, it's fairly simple. We've got -2 for the oxygen, and so +2 for the nitrogen. And so our nitrogen is being reduced from 5 to 2. All right. So we've identified our oxidation states and our half reactions. So we might as well write them out. So we've got zinc sulfide going to zinc 2 plus neutral sulfur. The sulfur is being oxidized here, and we've got a 2 plus charge sitting around on this side, so there's our 2 electrons to balance out our 2 plus charge. And then our NO3 minus is going to NO. And now we balance the single electron here by adding an electron. Now the oxygens aren't balanced. So regardless of whether it's acidic or basic, we're going to add water. So we've got 3 oxygens here, 1 oxygen here. So we need to add 2 waters to balance the oxygens. Now we've got 4 hydrogens, so we need to add 4 H pluses. And this is the reason why I should have waited to add the electrons. Now we should have added the electrons to balance the charge, especially too because that was obviously on the wrong side. Now is when we should have added the electrons. So we've got our 4 H pluses, and now all the elements are balanced. On this side we have 4 positive minus 1, so we need 3 electrons on this side to balance the charge. So now we have 4 negative charge plus 4 positive charge. So that's neutral, neutral, and so everything is charge balanced. And now to get our balanced equation, we need to sum the two, but we need to multiply by appropriate coefficients. So to get all the electrons to cancel, we need to multiply this guy by 2 and this guy by 3, as that'll give us 6 electrons in the end, right? And so then we can cancel everything and sum the two with the appropriate factors. So we're going to get 3 zinc sulfide on the reactant side from this guy. We're going to get 2 NO3 minus plus 8 H plus goes to 3 zinc 2 plus 3 sulfur. I guess I should have put 2 NO and plus 4 H2O. And so then this is our balanced equation in acidic solution. I'm just going to add one little note here and say the only difference between balancing an acidic solution and basic solution is in basic solution we would add OH minus to cancel out the H pluses, giving us water, and then we'd cancel out the water. So we'd add OH minuses to both sides, I should say. So that's really the only little difference for basic solution. I always remember it as acidic solution. You basically just follow the acidic solution, and then for basic solution you add OH minus. But here's our balanced expression. Here's the solution given. And that looks the same. So I'll say the solution is correct. Okay. All right, so complete this Bronsted-Lowry reaction, placing each product by its appropriate label. All right, so we've got HCO3 minus plus BRO minus. So a Bronsted-Lowry acid has a hydrogen, or is a species that can donate H plus. So in this case, it's this guy, as that's the only one with an H plus. So it's going to donate an H plus to this, and it's going to give us HBRO minus plus, oops, that's not true. It's going to give us just HBRO because we've got a plus charge with a negative charge, so it's going to neutralize it, or make it neutral, I should say. Plus CO3 2 minus. So the charges are all equal. The only difference is the transfer of H plus. And I ordered them this way because the question asked for them to be ordered this way. Right, so on the left-hand side we have an acid and a base, or on the reactant side, and then on the product side we also have an acid and a base, where CO3 2 minus is the conjugate base of our HCO3 minus, and HBRO is our conjugate acid of BRO minus, right? So in this case, this is an acid, and this is a base, whereas in this case, base acid. Okay, so a Bronsted acid is a substance capable of donating a proton, and a base is one that accepts the proton. So just identifying the proper agents. Then we get HBRO and CO3 2 minus. The HBRO is the acid, and the CO3 2 minus is the base. All right, so this looks good. All right. Sketch the resonance structures for the nitrate ion, NO3 minus. So just as a first guess, I usually just pop in the atoms around the central with their typical valencies. I shouldn't have done it that way. And remember, a Lewis structure is just representing each of the electrons as dots. And okay, so then if we just join up the bonds like this, it looks funny, but in the end, what we're going to have now, first of all, we need another electron popped in there because we've got a minus charge. right? So this is all neutral. So we need to pop in an extra electron. We can make sure that we didn't mess anything up by counting. So we've got 5 valence here. Each oxygen has 6, so there's 6 times 3. And then this is an extra 1 electron. So 6 times 3 is 18, plus 5 is 23, plus 1 is 24. So there should be 24 electrons. So here we've got 7 around nitrogen, oxygen, 5 around nitrogen, 6 around oxygen, and 6 here. 7 and 5 are 12, and 12 is 24. So we've got the right number of electrons. If we look at this structure now, so these are both 6, so they're neutral. This guy has a -1 charge. So the whole thing has a -1 charge, so that's good. But these oxygens don't have full octet, so they're not very happy. We can give them a full octet by taking away one of these electrons on nitrogen and say popping it over here, and then taking this electron and this one and forming another bond. And so then we would be able to complete all of our octets. So drawing this now in less of a hand-waving way, we'd have nitrogen, oxygen, oxygen, double bond, oxygen, and drawing dots for each of the electrons. Now summing everything up, so we've got 7 electrons here, 7 electrons here, 4 electrons here, and 6 here. So 7 and 7 is 14, and 10 is 24. So that's all of our valence electrons, so we're good. This guy has 7 around it, and it normally wants 6, so it's a -1 charge. This guy wants 7 around it, normally wants 6, so it's a -1 charge. Nitrogen has 4, normally wants 5, so it's a +1 charge. So we've got a bit of charge separation, but that's okay because we've got full octets. And the total charge will be -1 because -1 + 1 - 1 is -1. And so this looks like our structure. Okay, so now we're going to sketch the resonance structures. So we've got our oxygen, nitrogen, oxygen, oxygen. Okay, so our resonance structures just come from the fact that we can move this double bond up and then form another double bond and have the exact same, have the structure still be viable. So this is another viable structure. The only difference now is that the charges have moved. So now these ones are negative charged, whereas here these ones were. And then we can do this game again. So we can move this up and move this down and get another resonance structure. And again, the charges have now moved. But this is still viable. Now, resonance structures are not real. They're not actually happening. But what they do represent is that the molecule would exist in an in-between state of all three. Meaning, rather than any rather than two of these oxygens holding a -1 charge, each oxygen likely has roughly -2/3 of a charge. And the nitrogen almost certainly has a +1 charge, as it has a +1 in all three resonance structures. And so the electron density will actually be delocalized through the entire structure, which is what this represents. So it's still a handy tool for describing the molecular structure. So the hybridization of the nitrogen atom is sp2 in all cases, which means, so the reason why it's called sp2 is because it can form 3 sigma bonds. So the number of sigma bonds is just, I believe it's actually represented like that, sp2. So the number of sigma bonds it can form is just 2 plus 1 for the S, and then it forms 1 pi bond. Although in reality, we have something more akin to a third of a pi bond in each case. But so these are the sigma bonds, and which of the two lines I call sigma and which I call the pi is meaningless. I'm just pointing out, I'm just identifying what I am calling the 3 sigma bonds and the single pi. But you could call either of these two the pi, it really doesn't matter. Describe the orbitals involved in bond formation. So the sigma bonds will be more central to the vector which points between the two, whereas the pi bonds are actually above and below. And again, it will be more delocalized. So if we were to somehow be able to get a picture of the molecule from the side, the delocalized pi bond would actually be above and below the molecule. So that would be the pi orbital spread around the entire molecule, whereas each of the sigma bonds would be more local to the molecular structure. It would be more spread throughout like that. And this is kind of a rough picture for an sp2 hybridization as well on the nitrogen. Okay. So for NO3, there's our 3 resonance structures. The actual structure is in actuality an equal mixture. The hybridization of the nitrogen is the same, and there's a sigma bond and pi bond in each of the structures. Okay, so I'll say this is correct. And I think I'm gonna end it there. Okay, so that's all the questions for this session. If you enjoyed them, please subscribe to the OneClass channel. If you want to leave questions, follow the links below the video. This has been Jeff Krause for OneClass. Thank you.